I want to kick things off today with a little story. It's not exactly a fairy tale, but it does have four very distinct characters. Everybody, somebody, anybody, and nobody.
Ah, yes. The four horsemen of the corporate apocalypse. I know them well.
I bet you do. So here's the setup. There was this critically important job that absolutely needed to be done.
Okay.
And everybody was sure that somebody would do it. I mean, anybody could have done it. But, well, nobody did it.
And let me guess the fallout. Somebody got angry about it.
Furious. Because it was everybody's job. Everybody thought anybody could do it, but, nobody realized that everybody wouldn't do it.
Right.
So in the end, everybody blamed somebody when nobody did what anybody could have done.
Yeah, it's a funny little logic puzzle, but when you really think about it, it's actually a horror story about accountability.
It really is, and it's the perfect frame for what we're covering today. We are taking a deep dive into the Class 3 notes for software engineering, and we're focusing on the dark arts of estimation and delays. We're looking at why smart people miss deadlines, the tools like PERT and Gaunt that are supposed to save us, and a case study that, well, it burned through millions of dollars.
And if we look at the core theme here, it's really about how to stop being nobody. The sources today, which include chapters from Fred Brooks's incredible book, The Mythical Man Month, they're all trying to teach us how to structure responsibility so things actually get done.
Let's start right there. The Mythical Man Month. We're looking at Chapter 2. Now, I have to play devil's advocate here for a second. This book was written in the 70s. Software has changed, just a little bit since then.
A little bit, yeah.
Is Brooks really still relevant?
That is the big question. But the core idea in Chapter 2 is, I would argue, more relevant now than it was then. Brooks lays down this law that feels completely backwards. Adding manpower to a late software project makes it later.
Which just flies in the face of all traditional logic. If I'm building a house and I'm behind schedule, I hire more people to lay bricks and the wall goes up faster. Why is software different?
Because software isn't bricklaying, it's systems engineering. Brooks argues that the man month, this idea that you can just swap people for time, is a total myth. And it comes down to two main things.
Yeah.
Ramp up time and the explosion of communication.
Okay, let's break those down. Ramp up time seems pretty obvious. You hire a new person, they don't know the code base, they don't even know where the coffee machine is.
Exactly. But it's actually worse than that. Who trains the new person?
The people who are already on the team.
The people who are already late. So now your most productive engineers who are scrambling to hit a deadline have to stop what they're doing to teach the new hire how everything works.
So you're actually creating a negative productivity hit at first. You go backward.
You move backward. Exactly. That's the ramp-up tax.
Okay, that makes sense.
Yeah.
But you also mentioned a communication explosion. Is that just more meetings?
It's mathematical. And this is the part that, usually blows people's minds. If you have two developers, you have one line of communication between them.
Right, simple.
Add a third, you have three lines.
It's still manageable.
Sure. But if you have 10 people, you have 45 lines of communication. It scales by a formula, n times n minus 1 divided by 2.
So it's not linear.
Not at all. It's quadratic. It explodes. Every person you add doesn't just add their own work. They add a massive amount of coordination overhead to everyone else.
So by the time you coordinate what everyone is supposed to be doing, nobody has time to actually do it.
Precisely. The effort of syncing up completely outweighs the work getting done.
And this connects to the instructions in the notes for the discussion leaders. They aren't just supposed to read the chapter, they're supposed to find consensus.
Right. And consensus here isn't just, do we all agree with Brooks? It's, what are we going to do about it? The goal for the class is to figure out how to codify this into their own standards.
So if you know adding people to a late project is a disaster, what's your policy? Do you just refuse to add staff?
Do you cut scope instead? It's a really tough conversation to have with a client or, a professor. Sorry, we're late, so we're refusing any help.
It takes guts.
It does. But the alternative is what Brooks calls the mongrel portfolio, a project that's a mess of patched together code because there were too many cooks in the kitchen.
So let's say we avoid that trap. We keep our team small, but we still end up missing the deadline. This brings us right to Chapter 14, Hatching a Catastrophe.
I love that chapter title. It sounds like a monster movie.
It really does. And Brooks asks the one question that keeps project managers up at night. How does a project get to be a year late?
And the answer he gives is just. It's terrifyingly simple, one day at a time.
Oof. I feel personally attacked.
We all should. We tend to think projects fail because of some huge event, a hurricane, or the lead engineer gets poached by a competitor.
Some big disaster.
Right. A fire in the server room. But Brooks says those things are actually easy to handle because they're obvious. You can rally the team around a fire.
But you can't rally the team around a 10-minute delay.
Exactly. It's the termites, not the tornado. It's that tiny little slip. You say, oh, I'll fix this bug first thing tomorrow. That's a 4-hour slip. No one writes that down.
Because it feels embarrassing to report something so small. If I tell you I'm 4 hours behind, I sound incompetent. But if I tell you I'm a month behind, it's a crisis we can all solve together.
That psychological barrier is the killer. The notes call them silent slips. And the accumulation of those silent slips is what hatches the catastrophe. You wake up one day and realize you're a year behind, but you can't point to any single event that caused it.
So how do you stop it? The notes mention rigorous milestones.
Yes, and this is another key point for the discussion leaders. You need milestones that are binary. Done or not done.
Almost done is the enemy.
Almost done is a lie. 90% done is a lie. If the milestone is fuzzy, the slip can hide. The class has to agree on how they'll force these slips into the light. You have to create a culture where reporting a one-day slip is actually praised, not punished.
This feels like a perfect bridge to the tools, because if we're going to track these one-day slips, we need a way to visualize them. The slides introduce two heavyweights, PERT charts and Gantt charts.
The battle of the charts.
Let's start with PERT. That's Program Evaluation Review Technique. It looks kind of like a spider web, really, just boxes and arrows.
It does. It's a network diagram. And its main job is to show dependencies. Task B can't start until task A is finished. That's it. It just looks at the logic of the project.
And this is where we get the idea of the critical path. I feel like people throw this term around in meetings all the time, like, oh, coffee is on the critical path. But it has a very specific meaning here.
It really does. In that spider web of tasks, there are lots of different paths from start to finish. The critical path is the single longest path through that whole network.
Wait, the longest? Shouldn't we care about the shortest path to get it done faster?
That's the counterintuitive part. The longest path dictates the absolute shortest possible time the project can be finished. If that critical path is 20 days long, your project takes a minimum of 20 days, period.
And the scary part is, there's no slack.
Zero slack. If a task on the critical path slips by 1 hour, the entire project delivery date slips by 1 hour. This goes right back to hatching a catastrophe. If you don't know what's on your critical path, you let some minor task slip and you've just delayed the whole launch without even realizing it.
So PERT is for the logic. Then we have the Gantt chart. This is the one everyone knows, right? The waterfall of horizontal bars across a calendar.
Yep. Henry Gantt gave us that one back in the early 1900s.
Yeah.
And executives love Gantt charts.
Why is that? Because they look nice and organized.
Because they map to a calendar. A PERT chart just kind of floats in abstract time. A Gantt chart says, this specific task will be done on November 12th. It feels concrete. It gives you a sense of control.
But the notes mention a key feature of Gantt charts called resource loading. That sounds a little like corporate speak for overworking people.
It kind of is. A resource is usually a human being. And resource loading is when you assign those bars on the chart to specific people. And this is where Gantt charts show a harsh reality that PERT charts can hide.
Which is?
A person can only do one thing at a time.
Aha. Don't tell my boss that.
A PERT chart might show 5 tasks happening in parallel because they don't logically depend on each other. But if you only have one developer, you know Bob, and Bob has to do all 5 of them.
Then they're not parallel anymore. They're sequential.
Exactly. And the Gantt chart forces you to see that. If you see Bob's name next to 3 overlapping bars, you have a problem. You have resource contention.
So it seems like you really need both. PERT for the logic, Gantt for the human schedule.
That's the ideal. But the real danger is relying only on the Gantt chart because it looks so clean. It can hide those critical path dependencies. You might just move a bar around to make the schedule look good without realizing you just broke the logical flow of the entire project.
Speaking of breaking things, let's talk about a real-world example of all of this going wrong, the Chandler case study.
Oh, this one's a tragedy in software form.
For our listeners who don't know, Chandler was supposed to be this revolutionary open-source personal information manager. Think Outlook, but open and way better. And it wasn't started by some kids in a garage. The founder was Mitch Kapor.
And we can't overstate who Mitch Kapor is. This is the guy who founded Lotus. He created Lotus 1, 2, 3. In the 80s, that was the killer app. The guy is an absolute legend. He knows how to ship software.
And he had money to burn.
He put in $5 million of his own fortune, plus another $3 million from investors. So an $8 million war chest to start.
And he hired a dream team. I mean, the best of the best, top-tier developers.
So you have the legend, the money, and the talent. By all accounts, this project should have been a massive success.
And how long did they work on it for?
7 years. From 2001 to 2008.
7 years. And what did they actually ship?
Almost nothing. The notes describe it as a few barely workable releases. The project just died. It's a ghost town now.
How does that even happen? How does an $8 million project with Mitch Kapor at the helm produce nothing of value?
It is the ultimate example of hatching a catastrophe. It wasn't one big failure. It was death by 1,000 cuts. It was scope creep. It was perfectionism. They got bogged down in the details, constantly rewriting code to make it perfect instead of shipping something that was just good.
The second system effect that Brooks talks about.
Exactly. When you finish your first huge success, like Lotus, you have all these ideas you couldn't get to. So for your second system, you try to do everything, and you just drown in the complexity.
There's a whole book about it, right? Dreaming in Code by Scott Rosenberg.
Which I highly, highly recommend. It is painful to read because you can see the train wreck happening in slow motion. It just validates everything we've been talking about. They had no rigorous milestones. They let the schedule slip one day at a time until 7 years had just vanished.
It's a really sobering reality check. If Mitch Kapor can fail this spectacularly, your class project is definitely not immune.
Absolutely. It proves that talent and money are not enough. You need discipline, and you need a process to manage the inevitable delays.
Now, speaking of process, the slides take a hard pivot to something that seems really mundane but might be part of the solution. The wiki.
It feels mundane, but it's really about information architecture.
Fair enough. The slide has these open questions about the class wiki. Things like, should an edit summary be required? Should there be a librarian?
If we think back to that communication explosion problem, that NN12 formula, the wiki is the answer. It moves communication from being one-to-one to one-to-many.
Right. If I write the spec on the wiki, I don't have to explain it to 10 people one by one.
Exactly. But only if the wiki is organized. That's why that librarian role is mentioned. If you just dump information into a wiki, it becomes a digital junk drawer. A librarian makes sure that the team's group memory is actually usable.
And the edit summary requirement? That just sounds like nagging.
It's about accountability. If you change a major requirement, you need to say why. Otherwise, 3 weeks later, someone changes it back without knowing the history, and you get stuck in a loop. It's all about avoiding that one day at a time catastrophe by creating a paper trail of decisions.
There's another specific instruction for the discussion leaders here, too. They have to update the reading discussion notes page.
Yes. An overview of the reading, the decisions the group made, and any open items. It's forcing the team to commit their verbal discussion to a written record. Because if it's not written down, it didn't really happen.
That is a good life lesson in general.
Indeed it is.
Okay, we've covered the horror stories, the math, the tools. Before we wrap, we need to look at what's coming up. Homework time.
And the number one rule is always check the syllabus.
For Tuesday, January 27th, we have 2 key readings. First up is The Pragmatic Programmer, Chapter 8, and that chapter is titled Before the Project.
Which is great timing. Before the project is all about requirements gathering. It's about making sure you're solving the right problem before you even start drawing up those Gantt charts.
And the second reading takes us back to the Mythical Man Month. We're going all the way back to Chapter 1, which is called The Tar Pit.
The tar pit. It is one of the most famous metaphors in all of computer science.
So what's the image there?
It describes these massive prehistoric beasts, huge, powerful animals getting stuck in tar. And the harder they struggle, the more stuck they become until they're finally pulled under. Brooks compares large system programming to that tar pit. No one single thing pulls you under. It's the constant accumulating drag.
That's a cheerful thought.
It's a realistic one. It sets the stage for why we need all these estimation techniques in the first place. We're trying to build a bridge over the tar pit.
I like that image. So that's Chapter 1, The Tar Pit, and Pragmatic Programmer, Chapter 8 for Tuesday.
And as we sign off, I just want to circle all the way back to our opening riddle. You know, everybody, somebody, anybody, and nobody.
The cast of characters who wrecked the project.
We talked about the critical path, that unforgiving line of dependencies where any single slip kills the deadline.
Right.
Well, if everybody on the team assumes that the critical path is being watched,
Then nobody is actually watching it.
and then you end up just like the Chandler project. The critical path is the important job from our story. It requires a specific somebody to own it. It needs a specific name on that Gantt chart.
So the takeaway for everyone listening today is pretty clear. Don't rely on everybody. You have to be the somebody. Track the milestones, be vocal about the delays, and don't let that tar pit swallow you up.
Couldn't have said it better myself.
Thanks for diving in with us. We'll see you in the next one.